Async and await can make TypeScript code look clean, but they can also hide some of the most frustrating bugs. In this video, we will look at 15 real async mistakes, understand why they happen, and fix each one step by step. We start with async basics that often look correct in code review, but break the app at runtime. These first examples show why promise values must be handled intentionally. Imagine a profile service that loads the username asynchronously. Now we write the call as if it returned a plain string, and then we run the script to see what reaches the logger. Let's break down why the output looks wrong. An async function always returns a promise immediately, even if the final value is a string. The name exists later, but this code logs the wrapper right now. Now we fix the entry point by making main async. This lets us await the service result before using it, and when we run the script again, the terminal shows the actual name. The best habit is to look at the return type before using a value. If a function returns promise of something, await it before passing that value into logs, UI state, calculations, or other functions. A common startup task is loading configuration before the app begins. Here we try to use await inside a normal function, then we run the file and TypeScript rejects the structure. Let's explain the error in plain terms. Await needs a place where JavaScript is allowed to pause and resume later. A regular function does not provide that async context. Now we fix it by creating an async main function. The configuration is awaited inside that function, and when we run it, the startup mode is printed correctly. The best pattern is to make async startup explicit. Use an async entry function when the project is CommonJS style, and only use top-level await when your TypeScript and runtime configuration are built for it. Next, we look at async values being used like normal booleans or arrays. These bugs are dangerous because the code may run, but make the wrong decision. Imagine this is an authorization check before showing an admin page. The function resolves to false, but we forget await in the condition, so now we run it and see the wrong access decision. Let's unpack the behavior. The condition does not wait for true or false. It only sees that isAdmin returned an object, and objects pass truthy checks in JavaScript. Now we fix the condition by awaiting the authorization result. This time, the if statement receives the real boolean, and the terminal shows the correct denial. The best rule is simple. Never put a raw promise inside a condition. Await it first. Store the boolean if that reads better, and then make the decision. Now we move into arrays where async bugs often hide inside familiar methods like map and for each. The key idea is that array helpers do not automatically wait for async callbacks. Imagine an endpoint that receives product IDs and needs full product objects. We use map with an async callback, then run the script, and notice that the array contains promises instead of products. Let's look at the shape of the value. Because the callback is async, every mapped item is a promise. Map does not know that you wanted to wait for all of them. Now we fix the array by wrapping the async map result with Promise.all. This waits for every product request, and the terminal now shows actual product objects. The best approach is to treat async map as a two-step pattern. First, create the promises, then await Promise.all before returning, logging, saving, or sending the values. Here we have a notification script that should send emails and then print done. The callback awaits each send, but now we run it and see that the final message appears first. Let's explain the timing. Await is inside the callback, so it only pauses that callback. The for each call does not collect those promises, and main reaches done right away. Now we fix the script with a for of loop. This version awaits each email before moving to the next one, and done appears only after all sends finish. The best choice depends on the workflow. Use for of when order matters or calls must be sequential, and use Promise.all when independent async work can run in parallel. Now we are moving into concurrency mistakes. These bugs do not always crash the app, but they can make it slow or hide important results. Imagine a dashboard loading user data, orders, and notifications. These calls are independent, but here we accidentally await them one by one. Now we run the script, and the startup time is roughly the sum of every delay. Let's break down why this happens. Await does not just read a result, it pauses this async function until that promise settles. So 3 independent waits become a queue. Now we fix it by starting all 3 operations first. After that, Promise.all waits for the group. When we run it again, the total time is close to the longest single request, not the sum. The best practice is to start independent async operations before awaiting them. Use Promise.all when the screen or workflow needs all results before continuing. For practice, add one more independent loader with a 400 millisecond delay. First, predict the sequential time, then predict the Promise.all time, and check your answer by running both versions. In a batch import, we often want to see which records worked and which ones failed. This version uses Promise.all, so one bad record jumps straight to catch. Now we run it and only the failure message appears. Let's look at the behavior. Promise.all is fail fast, which means it gives you one rejected promise for the whole group. That is useful when partial data is not acceptable, but it is a bad fit for reporting every record. Now we switch to Promise.all settled, because this workflow needs a complete report. The fixed version separates fulfilled and rejected results. When we run it, we can see both the successful records and the failed reason. The best practice is to choose the promise helper based on the business rule. Use Promise.all when one failure should stop the whole operation, and use Promise.all settled when partial success must be visible. For practice, make record 3 fail 2. Then update the final output so it prints a success count and a failure count before listing the messages. Next, we are focusing on async error handling. These bugs usually come from promises that are created, but not actually handled. Here, a background payment sync fails after the main function has already moved on. The bug is that we call the async function but never handle its promise. Now we run it and the failure shows up as an unhandled rejection. Let's unpack the bug. Calling an async function starts it and gives back a promise. If that promise rejects and the caller ignores it, the error has nowhere controlled to go. Now we fix it by awaiting the async operation inside a try-catch block. This makes the rejection part of the current control flow. When we run the script, the error is logged in a controlled way. The best practice is to make every promise owned by something. Await it, return it to the caller, or attach a catch handler when it is intentionally running in the background. For practice, rewrite the fixed version with .catch instead of try-catch. This is useful for a truly background task where the main flow should continue. This registration handler looks protected because the email call is inside try-catch, but the email function is async and we do not await it. Now we run the script and the catch message never appears. Let's make the rules simple. Try-catch catches an async error only when the rejected promise is awaited in that try block. Without await, the code leaves the try block before the rejection happens. Now we fix the handler by awaiting the email call inside try. That connects the rejection to this catch block. When we run it again, the registration handler logs the controlled error. The best practice is to await async calls when their errors belong to the current error handling path. If the work is intentionally background work, attach a catch handler right where you started. For practice, add a newsletter step after the email step. Decide whether it should fail the registration flow or be handled as a separate background task. In service code, it is common to translate a low-level database error into a higher-level request error. This broken version throws a clean message, but it throws away the original reason. Now we run it and the cause is missing. Let's look at what was lost. The high-level message tells us the request failed, but it does not tell us whether the database timed out, rejected credentials, or refused the connection. That missing context is exactly what we need during debugging. Now we fix the wrapper by passing the original error as the cause. The outer layer still gets a clean request failed message, but the original database message remains available. When we run it, both levels of information are visible. The best practice is to preserve context whenever you translate errors. Use error cause for the original error, and add structured details when they help debugging without hiding the root problem. For practice, include a user ID in the high-level message and keep the original cause. The goal is to make the error useful for both product logs and low-level debugging. Now we move into object lifecycle bugs. These happen when an object looks ready, but its async setup is still running in the background. A constructor in TypeScript cannot be awaited, so async setup inside it can trick callers into using the object too early. Here the database client starts connecting in the constructor, but the caller immediately runs a query. Now we run the script, and the query fails before the connection flag is ready. Let's break down why this happened. The constructor finished immediately, but connect was still waiting on the timer. That means the type says we have a database client while the runtime state says it is not ready yet. Now we fix it by making creation itself async. The constructor becomes private, and callers must use database client create, which awaits the connection before returning the client. Now we run it again, and the query succeeds because the object is ready before use. The best practice here is to make async initialization visible in the API. Use a static async factory for clients, services, and repositories that need awaited setup that keeps callers from accidentally using half-initialized objects. For practice, add a connection failure inside create and return a clean error to the caller. This helps you design object creation as a real async operation, not a hidden side effect. Next, we look at shared state. These bugs are harder because each async function looks correct by itself, but the combination loses data. Shared mutable state becomes dangerous when an update reads a value, awaits, and then writes it back. This account example looks simple, but both deposits can read the same balance before either one saves the new value. Now we run it, and the final balance is wrong. Let's break down the timing. Deposit A reads 100, then waits. Deposit B also reads 100, finishes first, and writes 125. When deposit A resumes, it writes 150 based on the stale value. So deposit B's update is lost. Now we fix the account update by putting the critical section behind a tiny promise queue. The deposits can still be requested concurrently, but the read, wait, and write happen one at a time. Now the terminal shows the expected final balance. The best practice is to protect any shared state that crosses an await. In production, that might mean a database transaction, a real mutex, or moving the operation into a single serialized worker. The key rule is simple: do not let stale reads write back later. For practice, add a withdraw function that uses the same queue. Then run deposits and withdrawals together and check that the final balance is still correct. Now we focus on reliability bugs. These are the async mistakes that make apps hang, waste resources, or return stale work after the user has already moved on. Await does not include a timeout by default. If a third-party request never resolves, a CLI command or server handler can wait forever. Now we run this script and notice that it starts the request, but never reaches the done message. Let's break down the failure mode. Await pauses until the promise resolves or rejects, but this promise does neither. Without a timeout, your app has no way to recover from that stalled dependency. Now we fix it by racing the real request against the timer promise. If the provider does not respond fast enough, the timeout rejects with a clear error. Now the script exits cleanly instead of hanging. The best practice is to put explicit time limits around external work. Use request timeouts for APIs, job timeouts for workers, and clear error messages for callers. A slow dependency should fail predictably, not freeze the whole flow. For practice, change third-party requests so it resolves after 50 milliseconds. Then confirm that the same timeout helper returns the real result when the operation is fast enough. Calling abort does not magically stop every async function. Here, the user cancels a search, but the expensive worker never receives the signal. Now we run it, and the stale completion message still appears after cancellation. Let's break down the mistake. The controller exists, but expensive search has no parameter for the signal. Since the worker never checks cancellation, it keeps running like nothing happened. Now we fix it by passing the abort signal into every async layer. The wait helper listens for abort, clears its timer, and rejects immediately. Now the canceled search stops cleanly and never prints the stale completion message. The best practice is to pass abort signal through the whole async call chain. Check it before expensive work, listen for it during waits or requests, and stop promptly. Cancellation only works when every layer cooperates. For practice, add a fake ranking step after the search wait. Pass the same signal into that step too, and make sure cancellation prevents both search and ranking output. Finally, we look at a TypeScript-specific async bug. The compiler can help a lot, but only if we do not hide the real types from it. The AnyType can erase the most useful async warning TypeScript gives you. Here, a legacy API wrapper returns a promise of user, but the calling code treats the result as a real user. Now we run it, and the app crashes at runtime. Let's break down the type lie. Fetch user returns promise user, but any lets us assign that promise into a user variable. TypeScript cannot protect us once we throw away the real async return type. Now we fix it by giving the API wrapper an honest type. The function returns promise user, so the caller must await it before reading name. Now the terminal prints the expected user value. The best practice is to avoid any around async APIs. Model return values as promise of the real data type, and let TypeScript force correct awaiting. That turns a runtime crash into a compile time warning. For practice, remove await from the fixed version and check the compiler error. This is the behavior we want. TypeScript should catch the async mistake before the code runs. Now you know the most common async await bugs that junior TypeScript developers run into. If this helped you, like the video, subscribe to Dev Level Up, and comment with the TypeScript topic or bug pattern you want to see next.